Hello, everyone. Welcome to eTalks' newest episode with Dr. Christine Ehlig-Economides and Bushra Jan, our guest speaker and moderator. Dr. Christine Ehlig-Economides is a distinguished petroleum engineer and professor. She has authored over 115 papers and holds 4 patents. With a career spanning over 4 decades, she has spent 20 years working with Schlumberger and another 20 years in academia. A member of the National Academy of Engineering, her expertise includes reservoir engineering and complex well design. Currently, she focuses on research related to carbon dioxide storage, geothermal power generation, and blue hydrogen. And lastly, she was the first American woman to earn a Ph.D. in petroleum engineering from Stanford University. I think I said your last name wrong. Can you correct me? I know you told me beforehand, but I think I got used to the
No, I
economics.
think you did it fine, but I would pronounce Schlumberger, not Schlumberger. You've
Oh,
given it a German pronunciation, but
mm,
they're a bit French on that part.
all right. Thank you. Thank you. And Vishra Jan, who will be your moderator today, she's studying an integrated degree in engineering, arts, and science at Lee University, and she excels in sports, arts, and scientific pursuits. So Bishra Jan, will you like to get us started?
Yes, hello, I'm Busha Can. It's Lehigh University, but thank you so much. I'll be starting next year, and today we will have a discussion about the future of hydrogen transportation with Dr. Kristen Ehlig-Economides. Thank you.
So would you like me to start? Is it okay? All right. So I'm noticing that I've lost mouse control, but it's probably fine. Let's see if the slide will advance in just a minute. Uh, but before I do advance the slide, it's supposed to be moving. We've lost that too. Uh, I just want to thank you for the invitation to do this, and I hope people attending find it interesting. And I'm definitely looking forward to questions and interactions. Okay, so you know what? I do not have control. So can we figure out what's going on with that?
Would you like to press the next arrow button? Maybe that might work.
Mm.
On you, it's usually on your keyboard.
See, that's the problem. It's not.
Okay. Yeah.
I'm not even sure I can do that. Can So I don't know how much people have been following efforts to reduce carbon dioxide emissions. And most of these emissions, you probably also know, come from combustion. So this is a slide coming from IEA, the European Energy Association, or International is the I. And so we're looking at a contrast between a scenario that's kind of based on business as usual. If we keep doing as we are, then we're not going to see the CO2 emissions drop anytime soon. And then at the bottom of this is a scenario if all of these ideas actually happen in this way. And so the one that is of interest in part today is this one that's got a highlight box around it. And so CCUS stands for carbon capture, use, and storage. And so one idea is if we continue to combust, especially fossil fuels like coal and oil and gas, then we can try to capture the carbon dioxide emissions from doing that. And once we capture them, we can either use them or we can just store the captured carbon dioxide underground. And this is interesting to petroleum engineers like me because we understand the subsurface. So some people estimate that as much as 24% of this reduction could be accomplished through this process of CCUS. So now I'm going to jump a little bit to the idea of hydrogen. It seems like we're missing a slide that I would have liked to show, so I'm going to explain what it did show. But basically, the United States National Petroleum Council has done a study looking at various stationary sources of carbon dioxide. So this could be a coal-fired power plant, it could be refineries, but a lot of industry has stationary stacks. We used to call them smokestacks, but they don't put much smoke out anymore, which is a good thing. But they do put carbon dioxide out. And what this graphic shows is how expensive it is to capture carbon dioxide. So the previous slide looks good until we start to understand how expensive it really is to keep burning these fossil fuels and try to keep up with the emissions that causes. Well, what that slide doesn't cover, the graphic from National Petroleum Council, are the emissions from transportation, because that's not stationary. Transportation, you're moving, right? I mean, if you drive your car, it's not going to stand still. It's going to move down the highway. So capturing the combustion emissions from vehicles is particularly challenging. And so in the United States and in Europe and China, various parts of the world, there's a lot of attention to introducing battery electric vehicles so that people can transport themselves using batteries as the source of energy instead of gasoline and diesel, so these fossil fuels. So when you use a battery electric vehicle, you make no emissions from the vehicle. So that's interesting. However, the emissions still happen unless your grid, the electric grid, is entirely based on alternative energy sources, like, for example, the renewable energy resources like wind and solar. Or it could be nuclear as well. So these are not based on combustion, but still in the United States and in Europe, the majority of the electricity is coming from combustion of coal or natural gas. But that does at least represent stationary CO2 emissions, carbon dioxide, which you can capture, but it's expensive. So what we've been looking at is another type of electric vehicle, which is fueled with hydrogen. So these are hydrogen fuel cell electric vehicles. And they also don't have any pollution. So if you drive using hydrogen as a fuel, you are not releasing any emissions. And if your hydrogen is what we call blue hydrogen, which I'm going to talk about a bit more, then even generating the hydrogen has no emissions. So this represents a very important emissions reduction potential. So here you can see something important. Yes, is there a question?
Transport emissions as well, since most of the current hydrogen production today is extracted from fossil fuels and in a very maybe pollution heavy process, producing greenhouse gas emissions even during transport. And I had a question about like the infrastructure for green hydrogen instead.
Yeah, thank you, because I was definitely going to get to that. You're right. The other way to make hydrogen, besides, well, I'm going to show more than just blue hydrogen, but the favored way to make hydrogen is what you're mentioning. But you're going to use electricity to do that. And so if your electricity is only renewable, then your hydrogen becomes absolutely zero emission. But just like for the batteries, if your electricity to produce the hydrogen is not zero emission, then you're not totally correcting the emissions issue, even if you're trying to make the green hydrogen. So when you use electricity to make hydrogen, what you're trying to do is break the water molecule. You use electrolysis to do that. And it's really hard to break the water molecule. And so it takes actually a lot of energy. So I'm going to talk more about this. So I'm glad you brought it up. And we're going to see how that contrasts. So the code symbol that you see in the middle of this slide offers a link to the white paper that's mentioned on the slide. So if you want to capture that, you're welcome to do so. That's why I included it there. So I mentioned in the first slide that CCUS might represent on the order of 24% of CO2 emissions reduction. But transportation energy sector is 30% of US CO2 emissions. So if you can go after mechanisms to bring transportation to net zero, then you're going after 30% of emissions. So it's a very attractive target if we can make this happen. So we're going to compare different hydrogen generation pathways. So as Bushra mentioned, we'll also talk a little bit about the green hydrogen. But what this white paper showed is that you can make and you can refuel with hydrogen in the greater Houston area with costs that would be competitive with gasoline and diesel. And this is what I think people are missing, overlooking. And our study was done strictly with national lab tools. So it's pretty reliable, our conclusions. So it's interesting to comment on this, and I'm going to explain more about what SMR means, but SMR hydrogen, steam methane reforming hydrogen, if we refuel with that, we already drop CO2 emissions in the transportation sector by 20%. So it's already important. But if we go to SMR with carbon capture, then you can target that full 30%. So it's not small, the potential here. Here's where this slide is. So they somehow got out of order. Yeah, so this is the one that is talking about the costs for stationary point source emissions. And you can see that there are a few that are low cost. On the left, you can see maybe $10 to $20 per ton of CO2 that you capture. But on the right-hand side, you're getting way up over $200 a ton. And the thing about this process, it is being incentivized right now in the United States and also in Europe. But the incentives are coming from taxpayers. So we all need to realize that, yeah, it looks like tax incentives, we're not paying for it. Oh, yes, we are. And so what we want to do as we go into the energy transition is find solutions that are the most energy efficient and the least costly to the consumer. And so this is a reason why I find the hydrogen an attractive target.
Yeah, so in terms of like the current state in the energy sector with like hydrogen versus or like battery, for example, for our hydrogen transportation, there are many like maybe economical barriers like what we were talking about today. And would you say that that's mostly on like lack of infrastructure for transporting and storing hydrogen, or more on high cost of fuel cells and hydrogen
That's a great question because our study did not actually include in our cost estimates the cost of the vehicles. And that's where the fuel cell cost comes in. It covers everything else, but not the vehicle cost. The reason we left that off is because as long as the fuel cell vehicles are have so small use in the market, because California has made it possible for people to use fuel cell vehicles, but the rest of the country there's no infrastructure for refueling, so they're not sold. But if these vehicles are more widely used and produced, then their costs should be expected to go down. So the battery electric vehicles are also more expensive than your typical gasoline based vehicles at this point.
Yeah, add about like the green initiatives on like how it could like help the cost with like Europe being on the Green Deal, for example, like actually providing incentives to support these battery or hydrogen using cars or transportation. Right.
Right, but just remember that incentives like tax credits, any of these incentives are coming from the taxes we pay as taxpayers. So it's a little hidden how that works. But they are helpful because you know, people that cannot afford such a high price, say for a battery electric vehicle, but with the incentive they can, it starts to enable more of this technology to get in consumer hands. But just always remember that the taxpayers are why this works. So as to hydrogen generation costs, this is coming back to something that Busra mentioned or brought up. So some different ways to generate hydrogen are shown here. And so the ones on the left that we see here are around $2 a kilogram. And this is including the gray hydrogen that does not address any carbon capture. So you just make the hydrogen from methane, but don't worry about the CO2 emissions. But these two are worrying about the CO2 emissions. And what we see is it doesn't cost that much more to generate hydrogen from methane without CO2 emissions. Where if we want electrolysis using solar energy, this is the cost range for that, much higher. Electrolysis with wind, also much higher, not as high as the solar. Now, these data are coming from around 2019. So I'm guessing that this solar bar has come down a bit because solar power is becoming more and more reasonable in cost. So the hope is that these are going to become comparable sometime in the future. But for now, if we are seriously interested in introducing more use of hydrogen, it's rather more attractive to be thinking about using or generating it from methane. So this is talking about blue hydrogen is much less expensive than green hydrogen. So let's talk a little bit about these colors. So some people like the colors and some people rather put a number on the carbon intensity. So I'm okay with the colors. I can remember what the colors mean. But I will tell you that some people are not so fond of the idea. So if your hydrogen comes from wind and solar, then it has the color of green hydrogen and it is carbon neutral. Process is electrolysis. If it's strictly solar, people might call it yellow hydrogen. Now, if your hydrogen comes from methane, which is natural gas, and if you do take care of CO2 emissions, then you become carbon neutral. So these are different processes, and I'll speak a little more about these processes in just a minute. There is also turquoise hydrogen, and I think I have a slide that speaks to that a little bit. Different process, and it is also carbon neutral. Most of the hydrogen generated today is generated within 100 miles of where I sit. Certainly in the United States, but even more or less worldwide. A lot of hydrogen is generated on the Gulf Coast, and it is used in refining and petrochemicals. So this is also coming from methane. It's typically this steam methane reforming process. And it's called gray if there is no capture of the CO2 emissions involved in making the hydrogen.
Yes, but for transport wise, the target is always green, right? For zero emission, at least. So like energy loss and like hydrogen transportation as well. For example, a fuel cell you need to turn electricity into hydrogen, transport the refueling station, and also pump it into full. So for this, like, all this electricity and everything for the cars to be zero emission, I believe it should only be green hydrogen, right? That we're targeting.
Well, and that's where I would disagree, because if there are no CO2 emissions, then you can argue hydrogen is hydrogen. And so those cost comparisons that I showed on the slide just before this are very important at this point in time. Because if we really do want to make hydrogen available for transportation and we want it to be at a price that consumers can afford, then we should use a process that's affordable. And so that's why your questions are really interesting and important for me to answer them that way. Here here's the chemistry for anybody out there that can relate to this. So steam methane reforming is here. And so you put methane together with steam, and it reacts to form carbon monoxide and hydrogen. And then with the shift reaction, you end up with only carbon dioxide and hydrogen. And so if you let this CO2 go into the atmosphere, you're left with gray. But if you capture the CO2, then it becomes the blue. Other processes getting a lot of interest include this partial oxidation and also autothermal reactors. And these are attractive because they don't the CO2 emissions are easier to manage than for the SMR. But they both require that we have a new process unit that generates pure oxygen. So again, for those of you that like chemistry, there's a bit of chemistry on this slide. So to clarify between gray and blue, so if we have a hydrogen plant, what's coming in as feedstock is methane and water. What's coming out is hydrogen, and it has a stack that includes CO2. But it's not pure CO2 because you've combusted methane to make the steam, and so we've got nitrogen in the air that goes right through that process. So capturing CO2 from this is a relatively expensive process. But if you do that, then you can capture the CO2, put it in the subsurface, or find a user. And once again, same feedstocks with hydrogen as a product. And again, if we go with the green hydrogen, then if it's really green, you have to have green electricity coming in and water. And what comes out, it gives off oxygen and produces the hydrogen. And yes, just 2 days ago, I was in a hydrogen conference, and one of the talks was about whether there's going to be a market for the oxygen that comes from this electrolysis process, which could be helpful because if you could sell the oxygen in addition to the hydrogen, it can help offset the additional cost in energy. Because it really is energy intensive to break water molecules. It takes twice as much water to make hydrogen this way as with methane. Why? Because methane is CH4. So 4 of your hydrogen atoms come from the methane, and they don't have to come from the water. So in parts of the world where there's shortage of water, that could be a bit of an advantage as well for the blue hydrogen. So both gray and blue hydrogen require steam generation. And the most expensive part of the capture is if you use methane, burn methane in a boiler to make the steam for the reactions that I showed you a couple slides ago. So instead, if you use electricity to generate the steam, or if you use produced blue hydrogen to generate the steam, then you can really make this, you can see how straightforwardly you can make this a very low carbon intensity operation. So here's the turquoise hydrogen. Here you supply a lot of heat, so more than 1,000 degrees centigrade, but no oxygen. So this is generating hydrogen and solid carbon through pyrolysis. There's interest in this because the solid carbon that you get is very pure. And carbon materials are more and more interesting for electricity, for batteries, for composites. People interested in making hydrogen this way are also interested in marketing the black carbon, which may be graphene, so high-end carbon, and then of course the hydrogen. So we have a project now at the University of Houston that's a pre-implementation pilot to look into confirming what the study I mentioned up front suggests, that if we can get the stakeholders together, we can make it happen in Houston, that there would be hydrogen refueling. So the stakeholders we think are important are the people who make hydrogen, people who transport it. So this might be by truck in gaseous form, or it might be liquefied hydrogen. We need the refueling stations. We need vehicle owners, so people willing to own hydrogen fuel cell vehicles. And then the vehicle manufacturers are important as well, because they're not going to manufacture vehicles unless there's a market for the vehicles.
For like manufacturing as well, if you like you said, if you go into trucks, regarding, since a lot they make a lot more emissions with trucks than cars. I mean,
okay, so that's interesting too, because our study is focused on light and medium duty, and we think the market could be fleet vehicles, or it could be there's interest in using garbage trucks that are refueled with hydrogen, or mass transit buses refueled with hydrogen. But the DOE interest has focused much more on the heavy duty transportation. And so these are going to be your big trucks that maybe have 40-foot long trailers behind them. So heavy duty. For heavy duty transportation, the fuel that would be used would be probably liquid hydrogen, which has to be very, very, very cold. But for the medium and light duty, you can refuel with gaseous hydrogen. And so our study is focused on that element. And these tables at the bottom are highlighting some conclusions from the white paper. And so, for example, we conclude that in terms of cost to the vehicle owner per mile, the cheapest by far right now is battery electric vehicle. And I've driven them. They are impossibly cheap. It's so cheap to charge the battery in one of these cars.
For example, I mean, I should also let you know that we are on like 10 more minutes.
Okay, okay.
As well, hydrogen has more advantage in trucks, like weight-wise, than battery, right? In terms of like weight sensitivity.
Yeah, batteries are a bit more heavier than the fuel cell plus the hydrogen tank. That's correct. But what you see here is that gasoline and diesel vehicles are more expensive than the hydrogen. Hydrogen more expensive than battery, but both less expensive than gasoline and diesel. So that it could be an interesting thing to keep in mind. And in terms of emissions, the battery vehicles are more emissions than blue hydrogen fueled vehicles.
And they would take more time to fuel too, right? Battery. When we like think of bigger vehicles like trucks, it would.
Yes, yeah, they're not going to be practical for the heavy duty, the batteries. I think that's pretty much concluded now that we're not going to want to switch to batteries for the heavy duty. But for the medium and light, both hydrogen and battery may be options. So the project will include looking at the environmental and community risks and community impacts. And if everything looks like it's fitting together, then we'll be looking also at workforce development and environmental justice implications of this potential fuel switch. So these are very quick, but I would encourage everybody watching to do this. So do this and look at your hand and put your hand in front of the slide that you see. And what you're doing is mimicking what the existing natural gas infrastructure does in the United States. So this is not so attractive maybe in Europe, but in the United States, these are pipelines, and the pipelines go everywhere. So if we can make hydrogen from methane, you can make hydrogen just about anywhere you want to. Now, if you're going to put CO2 from your hydrogen generation in pore space, then we need to pay attention where the pore space is. So this gray and brown background represents suitable pore space where you could store CO2. So that's not quite everywhere, but certainly with a pipeline, you should be able to transport captured CO2 to pore space. And then if we put a grid of hydrogen hubs all over the country, then what we can do is possibly reproduce what we have concluded about the greater Houston area, that basically wherever you see a blue dot, you may be able to supply hydrogen, also competitive in price with gasoline. So what you start to see here is using that methane infrastructure. Use your hand. That's your pipelines. If you use that as a mechanism to ramp up hydrogen generation all over the country, you start to see a mechanism to go after that 30% CO2 emissions that I started talking about in the beginning.
I think it would be nice, like, concluding on these, like, points too. Like, regarding this, what would you say, like, your long-term vision, at least, and the role of hydrogen, using hydrogen, at least nationally, in the next decade?
Bridge, because all these questions you're asking about green hydrogen, I would see it as a potential mechanism to couple with battery EVs, so battery and fuel cell EVs together could offer consumers a reasonable mechanism to switch away from the combustion that's because of these gasoline and diesel vehicles. And we can use this methane infrastructure to ramp up quickly. But hydrogen is hydrogen. So anywhere where you can also start up electrolysis-based hydrogen or nuclear-based hydrogen. If you're watching Bill Gates, he's talking about introducing more nuclear. I can address that if you wish, but it's a very interesting idea, especially when you think about, in my view, this picture. So other hydrogen uses relate to electricity generation and industrial processes, in particular steel manufacture and cement plants. So if we enable hydrogen all over the country, then these are all potential prospects that look very interesting because they may be energy efficient alternatives to what we do today by combusting primarily diesel. So this is a summary. So that's the last one I was going to show. So I think a sustainable future depends on both hydrogen and electricity. It's worth mentioning as well that we will struggle if we only rely on electric vehicles for the light duty and medium duty, because they'll put a huge load on the grid. So considering hydrogen and electricity helps to address that.
Yes, and I just got a question about the last slide on what Bill Gates is saying about nuclear energy.
Yeah. Oh, what is he saying?
You just got a question.
Yeah. So what he's advocating, very interestingly, is also SMR, but his acronym stands for Small Modular Reactors. And I've been watching this for 20 years, the SMRs, because the nuclear engineers have been interested to introduce these for that long. And Bill Gates wants to see this happen, and also Dow Chemical may commission the first SMR. And now this is not steam methane reforming. This is small modular reactor. And these are very, very interesting because although they do still generate the waste from a nuclear power plant, what's different about them is that if we have a power failure or some kind of weather disaster or whatever, they cool a different way. They don't require pumped water. So if you're aware of what happened in Japan when they had a tsunami, it flooded the land and it stopped the pumps that cooled their nuclear power plants. And so they ran into huge trouble and emissions, and even nuclear emissions, radioactive emissions. But these small modular reactors will never do that.
Yeah, we just got another question from our viewer.
Okay.
Wouldn't hydrogen be also more dangerous to have in public use when it comes to immense vehicle traffic?
So I got it. Ultimately dangerous public view, but I didn't catch the last thing you said.
Wouldn't hydrogen also be more dangerous to have in public use when it comes
Ah, yeah, this is very interesting question. I love it. Because we were doing a webinar not too long ago, and this came up. So maybe this is what the viewer meant, maybe not, but people worry, if a hydrogen vehicle gets into a crash, are you going to have an explosion? Well, what someone who is very experienced in the audience told us, and it makes a lot of sense. If your hydrogen tank in a hydrogen vehicle is breached, the hydrogen is so light that it will escape directly up. And what I want you to contrast that with is if you have a crash in a gasoline vehicle and it breaches the gasoline tank, where's the gasoline? It's running all around you on the road, and it's on fire. And so it would appear that hydrogen vehicles should be safer in a crash situation than a gasoline vehicle is. But all vehicles are using energy, and in a crash situation, you may find that there is some fire going on, but it's just what she was pointing out, this participant, is that most of the hydrogen gets away and it doesn't stay there and burn right there by the car. But if that viewer wants to elaborate on his question, because maybe I'm not quite answering what he was after, or she.
Yeah, I think we got the same question twice actually from different people.
Uh-huh.
You got it. I'm getting messages.
Yeah, because people think about the Hindenburg, and everybody thinks about the Hindenburg. But the thing is, in light of what I just said, there are a lot of studies trying to figure out really what was burning. It may not have been the hydrogen. It may have been the body of the blimp. So we have to be careful about the Hindenburg. It may be very, very misleading.
Yes, all right. Thank you so much, Dr. Kristen. I think we have a few more questions. It's just regular e-talks questions we ask every one of our guests
Okay.
the talks. So the first question is, what is your favorite color?
Blue.
Right. So the second one is, what are 3 books you'd recommend to our viewers and audience?
3 books. Well. I should have done my homework on this, because I listen to books all the time, and there are just so many that I've so much enjoyed. Right now I'm listening to The Covenant of Water. Very long book, but a fascinating book. So highly recommend that if you're into very long books. Let me see, what have I also recently read? It's bad because my brain doesn't work like that.
But it's okay. One is okay. I can go on to the next question.
Sorry, what?
One is okay if you have only one in your mind right now. I can ask the next and concluding question.
Yeah, go ahead. I'll think about if any books pop into my, because I mean I so enjoy listening to books, but I always have trouble remembering the titles without thinking about it before the question.
And our third and final question is, what is a movie you didn't recommend?
A movie. Uh-huh. Yeah, because I haven't been watching movies lately. I don't get to movies so much anymore. So I mean, if I recommend a movie, it's going to be an oldie.
We love old movies and Argon, so that would be totally fine.
Yeah, yeah. Well, even that's kind of hard. There's a lot come to mind, but I'm not sure I'd say they're a favorite. I was a big fan of the movies that came around about baseball, though. Uh, so again, I don't remember the titles of them, but there were two or three that came out maybe 30 years ago. But they are interesting because if you just go to a baseball game, it could be pretty boring. But when you start to see what is really going on the field that isn't so obvious until you understand the game. So these were some of my favorite movies because they taught me something about baseball that never occurred to me.
Yeah. So I would like to put the mic to Krishna leading.
Yes, thank you, Dr. Christine, for this amazing topic that you educated all of us about. And we thank our viewers for joining us on this episode, and we hope you guys were able to take some information about hydrogen transportation today. So thank you, and we hopefully await everyone in our next episode next week. Thank you, and have a good day.
Thank you. Bye, everybody. And remember,
Yeah.
hydrogen is
That's
everywhere, easy from methane. Bye-bye.